This is our first video for Unit 3 and it's on scalars and vectors. What you need to be able to do when you're done watching this video is you should be able to draw vectors and tell me what a vector is and a scalar is, and then add and subtract vectors to find a resultant. Let's get started right away. Make sure that you're taking notes on this in your packet because you can use the notes on the video quiz that's at the end of this video. First, you might not know what a scalar and a vector is, so that's a good place to start, just to explain the difference between the two. So scalar measurements have a number that's followed by a unit. One example would be like 3 kgs. How a vector is different is that it has a number and a unit and a direction. So one example might be 3 kilometers west. A scalar measurement only has a magnitude that has to do with this number, how big or how small it is, but a vector has a magnitude and a direction. Some good examples of scalars are mass, like that 3 kg that's up there. I could have also wrote 3 seconds or 3 milliliters as a volume. Some examples of vectors would be velocity, like 3 meters per second west, or we've used -3 meters per second. That gives us direction. Displacement had direction, because that could be positive or negative, east or west, something like that. And force is a vector as well. And that's why we're talking about scalars and vectors today, because it has to do with force. When you draw a vector, you're going to use an arrow. And I think the best way to get the idea of this is just to look at an example. So here's our friendly guy from the Fat Moving Man, and I'm just going to call him Bob. So if Bob walks 5 meters to the right and then walks 8 meters left, we could represent this with vectors. So with a vector, it's really important to use a ruler to draw vectors, because the length of the arrow is going to be very important. That's going to give us the magnitude. So for example, we'd want one arrow being 5 units long and the other arrow being longer at 8 units long. So we said a vector has magnitude and direction, and the direction of the arrow, how the arrow points, that's going to give us the direction of the vector. So on this example, Bob walking 5 meters to the right, that's this arrow, and then walking, it's pointing to the right, so that tells us it's the arrow to the right. Then this arrow is pointing to the left, and it's longer, so 8 meters to the left. So the length of the arrow is important as well as the direction. Here's an example of a skydiver, and it's showing a lot of different vectors with the skydiver. You can see that his velocity is downward, his acceleration is downward, his displacement is downward, and his force is pointing downward as well, as a bunch of good examples. Now another term that we're going to be using a lot is called the resultant. What the resultant is the sum of 2 or more vectors. And the best way to get an understanding of that is just to do an example. Let's try one. So I'm going to use our example with Bob walking 5 meters to the right and then 8 meters to the left. So to find the resultant, you can do it 2 ways. You can do it as kind of a picture where you line up the vectors tip to tail, just like what's shown here. And then you find the resultant after kind of canceling this out. Then your resultant is a smaller vector than either of the two in terms of size, and the overall direction is pointing left. So the resultant is 3 meters to the left, and you would draw that resultant vector. Now another way you can find the resultant is with math. Let's check out that. So with math, what you would do is you'd add vectors that point in the same direction. So same direction, you want to add them. And vectors that are pointing in opposite directions, you want to subtract. And then how do you figure out which direction is the resultant? It's going to be the same direction as the larger vector if you have two vectors. So in this case, Bob walks 5 meters to the right and 8 meters to the left. So these vectors are in opposite directions, so we'd have to subtract. 8 meters left minus 5 meters to the right, and our final is 3, our resultant is 3, and that's 3 meters. The number with left is bigger than the number with right, so we'd say 3 meters left. And of course, you can draw this vector as well with a 6-in-1 or a ruler. What I want to do for the rest of the time is just do some examples, and hopefully these examples will set you on your way to success with your homework problem set. So example 1 says, find the resultant of the following displacement vectors, 50 meters east and 90 meters west. So first, I'm going to draw the vectors. And I'm going to do my best to put a 6-in-1 on my iPad screen. So 50 meters east could look like this. And 90 meters west would look like that. It's bigger, and the arrow is pointing in the opposite direction. Now to find the resultant, since these are opposite directions, you would subtract them. 90 minus 50 equals 40 meters. And to figure out the direction, we'd take the bigger one. So 40 meters west is our resultant. And how we would draw that is something like this. Notice that the arrow is shorter than the 50 meters, and that's because I used a 6-in-1 to draw it. Let's try the next one. Find the resultant of the following velocity vectors, 35 meters per second north and 25 meters per second north. I'm going to draw those first. And you might be confused because I didn't draw this north going up and down. And that's okay, as long as you are consistent with your directions. Now this one would be 25 meters north, 25 meters per second. And since these are in the same direction, to find the resultant, I want to add them together. So 35 plus 25 meters per second equals 60 meters per second. And because this is a vector, I need the direction of north. And now I want to draw the resultant. Which will look like this. The length of those two added together. Let's do a couple more examples. Here's one with an airplane. A plane flies with an airspeed of 50 miles per hour east, with a tailwind of 40 miles per hour. If you don't know what a tailwind is, that's a tailwind that blows with the movement of the plane. So the tailwind would be like that, and the plane is already moving. Let's draw the vectors. So our airspeed vector is 50 miles per hour east, and our tailwind is 40 miles per hour east. So, since these are in the same direction, we would add them together and then draw our resultant vector. Okay, let's try another one. What is the ground speed of an airplane flying with an airspeed of 100 miles per hour west into a headwind of 20 miles per hour? So, we're driving flying 100 miles per hour west, and there's a headwind of 20 miles per hour east. Let's draw the vectors. Here's our 100 mile per hour west. and here's our 20 miles per hour east, drawn with a ruler. Now what would the resultant be? These are opposite directions, so you'd have to subtract them. That gives us 80 miles per hour. If you look at the two, west is bigger than east, so our resultant is 80 miles per hour west. Let's do one more example. This example looks a lot like your problem set, and I just wanted to walk through it so that you feel comfortable with your problem set. Billy walks 10 miles per hour left, or 10 meters left, and then turns around and walks 2 meters south. That doesn't make any sense. So we're going to say 2 meters right. Draw a vector diagram for the two directions of walking. So, all I would do for part A is draw those two vectors. 10 meters to the left, and 2 meters to the right. Then it says, use vector addition to find the resultant vector. So for that, what you'd have is 10 minus 2 equals 8. For part B, it says, what's the magnitude? The magnitude is 8 meters. And the direction is going to be what? Which one is bigger? Left is bigger. And then finally for part D, it says draw a vector that represents the resultant. So we want it to be, I'm making this one 8 centimeters long, and it's going to be pointing left. And that's it. Your problem set is just doing about 5 or 6 of those. Now the question is, where are we going with this? Why are we learning this now? And it's because we're going to be doing what's called free body diagrams, where we take all of the forces, different types of forces that we learned yesterday, and draw a diagram with vectors to represent the forces. So what you can see on this one is that there are 4 forces: gravity, normal force, applied force, and friction force acting on this box. If you look at the size of the arrows, normal force and gravity cancel each other out. But applied force and friction are in opposite directions, and they're not the same amount. The applied force is greater than the friction force. So what's happening with this box is it's being pushed to the right. And we're going to figure out how I was able to tell that within the next couple days. Alright, let's take that video quiz and get started on our problem set.